See how we can use examples from the lecture and improve on it to see whether that fits your needs. So let's start with the one of the examples we covered last time, which is bounce ball. And bounce ball is actually from the lecture notes. If you go to the lecture, there is a PDF file and you can find the program. You can copy and paste it here and try to run it in your own Eclipse. And let's run it and see how it works. So we'll run it. Just a second. Let me remove this breakpoint first. Run it and see how it works. It looks like a bouncy ball. And let's dive into this program and see how exactly it works. So the first thing you want to see is the run method, which is the entry point of the whole thing. And setup, if you go into this, basically it draws a ball and then put it in this position here. So that's simple. And then there is a loop. We don't care about the loop condition right now, but let's just take a look at what this does in this loop. It moves the ball a little bit.
Then it delays a little bit.
And then it delays a little bit. And then it moves the ball a little bit, delays a little bit. Move the ball a little bit, delays a little bit.
And then you...
How much does it move every single time? You can see that each time it moves by this much. And each time it moves, the y keeps changing. The x doesn't. Why keeps changing? They want to simulate the gravity pulling the ball down so that when the y direction on the up and down direction, it wants to increase the speed of dropping more and more each time you try to move it. So we can run it and see how it works. So let's close this. Run it again. So y initially is 0. So there is no speed on the y direction. But each time it tries to increase it by a little bit, which is 3. So we'll run it, and then we'll see that it moved a little bit. And x is 5, y is 3. And then we run it again. So next time it moves it, y is increased a little bit. No longer 0 anymore, it's 3. So we gain a little bit speed on the y direction. Now it moves a little bit on the down direction. So as you can see that you just keep running this. You just keep running this, it gives you an illusion of something continuous when it runs faster. When in reality, it's actually basically a jump, 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 jump. So that's how animation is created. Well, think about it in this case, that in your case, the assignment you were given, the breakout game, the ball also moves, but it doesn't have gravity. It moves in the direction that the speed never changes. So in this case, you probably can change the way it behaves and try to see whether you can simulate and change this a little bit to get what you want. So first thing you notice that the speed never changes. There's no gravity. So well, we can just remove this gravity. We remove this gravity. And then there's no change in this gravity. Okay, remove this gravity and now I run it. What will happen? I will run it.
That's not good.
Okay, so it disappeared. Why is that? Well, as you can see, the first step in the initial value, these two are given what value? So at the initialization point, this x velocity is big X velocity, which is 5. And then the y velocity is 0. So it gave you an x direction, the horizontal direction velocity of a certain value, but there is no direction on the y value. You can get the chair there. So that explains why it moves horizontally all the way. And you want, well, first of all, it looks like it moves very slow. And to change that, you probably can change this and make it faster. So instead of 5, let's give it a 50. See how it works.
Oh.
Whoop. It finished. Well, the thing is that you want to bounce, right? You want to bounce around. And why didn't it bounce? Remember, it actually bounces over the floor, but it doesn't bounce this. Why is that?
Because you didn't set the boundaries to that, so you can't.
So let's go back to the loop. Each time after it moves the ball a little bit, it checks for collision. And let's see how this thing is implemented. So check for collision is implemented in here. So in what condition it checks? It checks the ball's y position. So basically it checks the height of the ball and see whether that's below this part. Get height is the y-axis in this point right here. And then get height minus
the diameter
of the ball, which means that if the y position of the ball is below this position, which means that the lower boundary of the ball is touching here, then it triggers the action. What's the action? The action is that all of a sudden you have a speed which is changed in y direction, but not in the x direction. So why it bounces over here? Because it's checked the boundary decision here, but it never checks the boundary decision here. So if we wanted to bounce over here, we need to add a check here so that it knows, well, if we see the right-hand side wall, we want the ball to be able to bounce back. So as you can see, this is probably similar. So we can do a similar thing. Else, if ball get instead of y, we want to get the x direction. So if its x value is near here or on this part, which means that it's greater than a value which is so this one is get width minus diameter of the ball. So which means that the ball's right boundary is touching this wall right here. And now we want to do something. And this time we don't want to change the velocity of the y direction. Instead, we want to change the velocity of x direction. So we have similar things to do. X velocity equals minus x velocity. Okay, so take a look at this. This is more complicated than this one. Why? So change ball's y velocity. So this basically give you an opposite direction. At the same time, it tries to multiply a factor, and this factor is 0.9. Why is that?
Because it reduces the speed.
So the example is bouncing ball, and it tries to simulate the gravity pulling the ball down. At the same time, each time it bounces, it loses certain energy, it loses a portion of energy, so that the bounce goes lower and lower. And that's why it multiplies a factor which is 0.9 that's greater than, smaller than 1 here. So each time you change the direction and then you make it a little bit smaller. Here we don't need that. In breakout, the ball never loses its velocity and never have gravity. So we don't need that. So in this case, we just change the direction of that of the velocity, and then we don't need to reduce the speed due to bouncing. So now we change the direction of the velocity. But what about this part of the code? What does this do? Well, if you go back to the lecture video, the lecture actually introduced this part. So remember that the animation is implemented by jumping. So you wait for a period of time, and then you move the ball to a distance, and then draw a ball there. The moving may happen from here to here. And then in this case, if the ball is moved from here to here, you are out of the bounds already. In this case, you want to be able to draw the ball here. So that's what this is about. This is moving the ball back into the proper boundary. So the difference it calculates is that this is the upper edge of the ball. So this part is the upper edge of the ball, and then this is get height diameter, which is somewhere around here. So if the upper edge of the wall is lower than this line, it tries to go back above that line. So that's how this comes from. And we can have a similar thing here. So double diff, and instead of using y, we can use x, and then get width, and then we ball move. And then now we need to be careful. This is on the x direction instead of the y direction. Y direction doesn't change at all. And then we don't move y at all. Okay, so now it bounces onto two walls. So it bounced against this wall and it bounced against this wall. And we still have two walls to care about. This one and that one. So it bounces off all four walls. So we see this one checks the bottom, this one checks the right edge.
So you need the left side and the top.
Yes, left hand side and the top. The sequence doesn't matter. So what if you want to check x against the top? How do I check this? What do you suggest I put in here? So remember that the ball x.
It has to be greater than 0. No. If it's less than 0.
Yes, it's less than 0. Why? Because this position, this upper wall, the x value here is 0, and the ball being higher than the upper wall, meaning that the upper edge is higher than the 0, which means that, well, no.
Then it's out of.
No, wait. Y. We're talking about the upper wall here. Y is less than 0, and then we are against the upper wall. So which means that y velocity need to change.
Wait, but isn't it 0 plus ball diameter?
So why do we need to check this here instead of just using get height? Because this value is not the center of the ball, it's the upper edge of the ball. So the ball is like not a single dot, but has some volume in it. And then if the ball like this big, and the y direction is around here. So if the ball is at this position right here, we want to check the y value, which is here, is greater than get height, which is here, minus the diameter of the wall. And that's when the wall is out of the bound. You want to check that the lower bound of the ball, which is get y plus diameter, is greater than this. So we can change it to another thing, which is plus so this is basically the same with and I think this might be easier to understand. Why? So remember, this is the upper edge. This get y is the upper edge of the ball. So if the ball is like this big, and the get y is this position, and then when you try to check the boundary against the lower floor, you want to be able to compare the lower edge of the ball, which is this evaluation, this expression, against the total height of the window. So that's a condition you check. That's a condition when the lower edge of the ball touches the floor. And then you go into this logic of trying to reverse its direction. On the other hand, here, this by itself is already the upper edge of the ball. And you don't need to have another adjustment to check against the top edge of the window. 0 is the top edge of the window. So you can just go in and then change its direction. And of course, we have to do the similar kind of situation here. So how do we do here? So suppose this is this edge is this edge here represents the upper edge of the window, and the ball is around here. Let's see. Let me run it and just let me run it so that I can have a better description of it. So you see this ball here, and then we're talking about this branch here. When does this branch came into play? So the ball get y smaller than 0. Ball get y is the upper edge. The ball's upper edge. This one is smaller than 0, meaning that the ball is somewhere around here. And if we calculate the upper edge of the y, how much is actually get out of the upper edge? And then we want to use that and times -2, and then move that. And that number is very similar to here, but without the adjustment of this. So we can actually have a similar, very similar formula. Diff get y, and then get height is the lower value, and the upper value here is 0. Hello. How was your water break? They're fixing it? I mean, they're fixing your...
Oh, yeah. It's really noisy. Oh.
They turned off all the water.
They turned off all the water.
But they did give us some warning, so then Jennifer was like, Mommy, the water's not working.
Okay, so you're right, but
just
so I recorded this part, so you can go back home and review this video after I upload it to YouTube. Anyway, so give you a recap. What we're doing is basically using the bouncing ball example used in the lecture. Remember the bouncing ball example the lecture showed that you give a ball and then it bounces over the floor. And then we changed several parts. The first is that we remove the gravity, since that we don't need to pull the ball down. And then we remove the bouncing factor, since that each time it bounces, we don't want to it to lose energy. We want the ball to bounce forever, so we remove that. And now we're talking about bouncing off. Instead of just the floor, we bounce off this wall. And now we're talking about how to bounce off the top wall. And the top wall, we're composing a diff similar to this one. So it's the same here, that we are using y. And then the bottom wall is, the y value of the bottom wall is get height. But the y value of the upper wall is 0. And then remember that we don't need to adjust for diameter of the ball, because this y is the upper edge. So basically it's like that. And then this,
So isn't it just 0?
this is just that. So we don't need the another variable at all. So turn out we don't need that. So we can just use ball.move -2 times ball.getY, and then 0. Wait, no. So we're changing the y direction instead of the x, so it's like that.
Wait,
We're changing the y direction instead of x, right? So that's why I gave it to this. And now we can use very similar ways to check on the left-hand side wall, which is basically change y to x. So else if, now we check for dot get x against 0. So this is bounced against this wall, left wall. And then if we have that, we have a very similar situation where we want to change the velocity of x. And then we also want to adjust for overshooting. Okay, so now we have 4 walls. Our board bounces all 4 walls, and let's see how it runs. So first I stop this and then start it again. Let's remove this. So it keeps bouncing left and right. Why is that? Because we have no speed on the y direction. There's no gravity and there's no speed on the y direction. So what we can fix is, make it more interesting, is that we can just give it some initial y speed. So we just give it like maybe 7. And then let's see how it runs.
Yay! Oh, that's basically what you're using. But you just now have to make the bricks like go away.
I think there is some problem with my left wall checking.
It doesn't bounce all the way to the wall.
Yes. Let's see whether I can make it slower to see whether that's the case. So x is maybe 5. Make x 5 and then y 3. And let's see. Let's see how it goes this time.
It's like velocity, I think.
So this time it moves really slow, but it does bounce.
Oh.
Yay.
I guess it's right. It does bounce off the left-hand side wall.
You know what
Yeah,
I
it
was
does.
doing before? I was doing like that or something. That's why I was so fast.
Okay, questions. So as you can see that we changed the behavior by several things. The first is that we remove the gravity so that the ball doesn't pull down. And then second is that we remove the bounce factor. The bounce factor takes away a little bit of energy each time it bounces off. We remove that, so the ball will just bounce forever. And then the third thing we did is that the original program just checked for bouncing against the floor. Now we check against all 4 edges. Now it will just bounce forever. And then that pretty much fits your needs of whatever you have right now, which is the game you're trying to program. Okay? And so that's that.
then you have to make the bricks disappear when you.
Yes. So I'm just letting you know how to go about doing that. And
There's a thing that you can move. Just you can check where the ball is and if it's hitting a
so
object.
this PDF has lots of information which is valuable. So this is a starter, and hopefully you already fixed that. And we'll talk about the paddle just in a second. And then create a ball and bounce off the walls. This is essentially what we just showed in our example. We have a ball, now it bounces off the wall. And read this part very carefully because it talks about check for collisions. We check for collisions against 4 walls, but in your assignment, we have collisions against walls and bricks and pedals. And this section tells you how to check collision against all the kind of different things.
Just do that.
So this is how you do that. And remember that the breakout game, you don't check collision against the bottom, the floor.
Because you lose.
Yes, once the ball passes that, you lose. Which means that you do need to check for that condition, but you don't change the direction of the ball movement, you declare you lose.
Check for collision on the floor and then display you lose.
Yes. So that's run direction. But anyway, this part about how to check for collision against different things is very important, and do read it and use my example to guide your own programming. And so now that's one example we covered using the bouncing ball. And let's see another example used in the lecture. So if you go to the Stanford lecture website and go to lecture 11, lecture 11 was talking about event-based programming, which allows you to write a program to react to your mouse movement. And here there is an example. Graphic events example. And there are several things in here. And today I'm going to talk about one last example, which is the mouse tracker. So I already copied and pasted this file into my environment here. So where's my mouse tracker? Okay, so this is a mouse tracker. And let's see how it runs. So you see, once the mouse moves into this region, it shows a label, and then the label value changes while you move your mouse. And remember, in the lecture, the teacher tries to move it to 0 and 0 and see whether it can get there. It seems that it's very difficult for me to get there. But anyway, so it tells you how to track for mouse movement. So here it has a add mouse listeners, which means that it tells the program to listen for mouse movement. And then here, this method is called every time there is a movement. And every time there's a movement, it changes the label value. We can do something similar actually here. Suppose we have a ball. So we want to have a ball. So this is a ball. We copy the ball. Copy the ball here. And then, so in addition to the label, we have a ball. And then we need to put the ball somewhere. And we just copy everything here. We don't care where it is. So now we add a ball after that. So x start. Well, why don't we just put it 0? I don't care. I'm just playing around here. And then another 0. The diameter of the wall, let's say maybe 5.
5 is small.
Pick a number.
10.
10, okay. So you like 10. And then other opinions? Somebody needs 20 or whatever. So, and then we just draw the ball here. And then every time the mouse moves, we move the ball to the mouse, wherever that mouse is. So how to do this? We set the location of the ball. So we can set x to whenever this is. This is a mouse move event, which tells you where the mouse moved to. So e dot get x and e dot get. So this is set x. No, there's no set x. Oh, I remember. It's set position. So set location. Okay, set location. We have x and y, so we use e dot get x and then e dot y. Okay, so now what it does? Take a guess.
It'll move the ball to the new location.
Yes, it will move the ball to the new location. So now I run it, and when you move the mouse, you will see that the mouse is dragging a ball around. So now you see actually whenever you see this mouse is dragging the ball around. What if you have only one direction you want to drag? You don't want the mouse to follow it everywhere, but you want the ball to follow it in some location.
You can set only you can set a Y position.
Yeah, so basically you can do something like this. Private double level equals, pick a number, I don't care, 300, and then set the Y location to be 300, and then we don't change Y at all. The Y direction is always at level, and of course level. Now I run it and see what happens.
So you can only keep it on the same level. But
yes, but you can move it left and right. That's your pedal right there.